Chapter 9 is pretty short. Basically, it's taking your Lewis structures, and once you've drawn that, figuring out the shape of a molecule. Because one thing we have to remember about when we draw it on paper, it's flat. But they're not flat, they're three-dimensional. So you can actually figure out the shape of a molecule by looking at the central one, the one in the middle, and then what's bonded to it. How many pairs, how many bonds does it form, and how many lone pairs it has. Okay, so they call that molecular geometry. All right, and the structures, like I said, when we draw them, we pretty much draw them flat, but it's not really denoting their shape because, again, they're not flat, they're not two-dimensional, they're three-dimensional. So there's ways you can figure out their shape, and again, it's looking at how many bonded pairs they have and how many lone pairs they have. Okay, in this case, this is carbon dioxide. It has two bonded to it, no lone pairs. This is linear. And there's a chart, and I'm going to show it to you. There'll be a copy of it for you to run off. This one, there's actually a lone pair right here. So instead of being linear like this, it gets bent, it's called. Okay, here you have one central and three bonded to it. They all spread out evenly, and that's called trigonal planar. Here you actually have a lone pair right here with nitrogen, and it squishes them closer together. So they're not trigonal planar, they're trigonal pyramidal. And then I don't have a tetrahedral on here, but I'll show you that one here. Okay, we're going to pretty much do the common shapes for molecules where you have a central atom and two or three atoms connected to it. Okay, and again, the hardest part is drawing the Lewis structure. Once you got the Lewis structure, it's really easy to do the shape. Okay, and again, it's determined by the central atom and how many things are bonded to it. Okay, so here we have linear, we have trigonal planar, and these are giving you the angles between them. This is called tetrahedral. Tetrahedral is where you have one in the middle and four bonded to it, like CH4, methane. And then here's bipyramidal and octahedral. We're not going to really deal with these two. We're just going to stick with the common ones. Okay, so the thing to remember is electron pairs are going to push each other as far apart from each other as possible. So they're going to situate themselves so that they're even. Okay, and that's where you come up with these angles. Okay, and again, remember, we're doing three-dimensional. We're not doing flat. I mean, if you did this one flat, it'd all be 90 degrees, but we got to take in front of and behind as well. Okay, and to do that, there's a model. It's called VSEPR. It stands for valence shell electron pair repulsion. I think you have to say it fast, otherwise you get stutter it. But it's very simple. Basically, what you do is you look at the central atom, how many pairs are bonded, and how many lone pairs you have. And from that, you can figure out the shape. And again, I have a chart for you to use. Okay, if you look at this guy, we have three bonded to it. And it doesn't matter, don't worry about the double bonds and triple bonds, you guys. It's just there's 1, 2, 3 bonded to the central atom and one lone pair. Okay, so if I look this up on my chart, what I would find out is 3 and 1, this is trigonal pyramidal. So again, all you have to do is look at how many bonded pairs, 1, 2, 3, and how many lone pairs. That's all you're looking for when you do this. Okay, and again, I'll have another video to show you. Okay, it basically, the VSEPR, you're looking at the valence shell, the electrons on the very outside, and then how they, again, electron pairs want to be as far apart from each other as possible. Here's some balloons to show you. We got a linear, we got a trigonal planar, here's a tetrahedral. I think I used to make my kids do this in high school, and I don't think they ever really liked it, but you know, you got to blow balloons. Okay, so here's the ones. We got linear, okay, we have trigonal planar, we have tetrahedral, we have trigonal pyramidal, and we're not, or these last ones, we're not going to worry about, the 5 and 6. We're just going to worry about these top ones, okay? And again, I have a chart for this for you to download so you have one. But really, all you're going to do is you're going to look at the guy in the middle and how many are bonded to it, okay? This has 2 bonded to it, so it's linear. This has 3 bonded to it, trigonal planar. This has 4 bonded to it, tetrahedral. None of these have lone pairs, okay? When you have a lone pair, okay, if this is my Lewis structure for ammonia, this lone pair pushes these 3 guys closer together. So it's not going to be planar. Instead, this lone pair up here is going to make it pyramidal. So it'll be trigonal pyramidal. And again, it's just reading this, the chart. Okay, so when you do VSEPR, you draw the Lewis structure, and again, that's probably the hardest part. And then you look at it. Okay, how many are bonded to the middle guy? How many lone pairs do I have? And then that tells you the shape. So it's really very simple. It sounds complicated, but it's not very hard. Okay, and they're in your book. 9.2 and 9.3 show you them. And again, I have a chart for you to use as well. But really, all you're looking at is the guy in the middle, bonded 3, 1 lone pair. That's what you're looking at. Okay, and here we got them. One thing to remember, if there isn't a central atom, like if you're doing HCl, that has to be linear. Okay, there is no central atom. So if there's only 2, it's always linear. But here's carbon dioxide is linear because when we draw it out, we got 1, it's 2 bonded to it. It doesn't matter that these are double bonds. It's just that 2 oxygen are bonded to it, no lone pairs. Don't worry about lone pairs on these guys because they're not the central atom. So this would be 2 and 0. Here you go. 2 and 0, linear. Okay, 2, 0, linear. Okay, again, remember if it's only 2 elements, it's always linear. Okay, oh, I put that here. If there's only 2 atoms in the molecule is always linear. Okay, so you don't have to do it if it's only 2. There's no shape to it, it's just linear. Okay, here's another example of a trigonal planar. Okay, here is boron fluoride. We've got them, you know, 1 boron and it's 3 bonded to it, no lone pairs. 3, 0, trigonal planar. Here we have nitrogen dioxide. Okay, we have a lone pair here. So we have 2 bonded and 1 lone pair. 2 and 1 is bent. So again, all you do is look at the central atom and look what's going on. 2, 1 lone pair. 2, 1 lone pair bent. Here, 3, no lone pairs. 3, 0, trigonal planar. Okay. Here's some tetrahedral ones. Again, here we got carbon with 4 bonded to it. 4, 0, tetrahedral. Here we've got NH3. Again, we got that lone pair. 3, 1, trigonal pyramidal. Here we got water. We have oxygen with 2 lone pairs and 2 bonded. 2 and 0, 2, 2, bent. So again, all you do is look at when you draw it, look at the guy in the middle. 4 bonded to it, no lone pairs. 3 bonded to it, 1 lone pair. 2 bonded to it, 2 lone pairs, and that tells you shape. So that's all you need to use is this part of the chart. The bonded, lone pairs, shape, okay? And that's pretty much, you know, what this chapter is about. The non-bonding pairs, you guys, have more repulsive power, so they push things closer together, okay? Here you have carbon with its hydrogen, and because they're all hydrogen, they're all equally spread out, so the angle is 109. But when you have nitrogen, this lone pair pushes them just a little bit closer together, so it's only 107. And then here in oxygen, when we have water, we have 2 lone pairs, so it pushes them even closer together. So lone pairs basically have more repulsive force, so that's why you have the different shapes. Okay, you can expand out on it, and again, I was saying there's a 5 and there's a 6. We're not going to deal with that. We're just going to go through where there's 4. Okay, that's what we do Lewis structures for. That's what we're going to deal for. There is expand upon that, but we're not going to worry about it. Okay, again, here's what they call when you have 5. And again, there's got to be some special cases going on for this to happen. So we're not going to deal with it. It does happen. Wanted to show it to you, but I'm not going to worry about it if you don't understand it all. Okay, and here's if you had 5, you could have 4 different shapes. 5 with no lone pairs, 4 with 1, 3 with 2, 2 with 3. And then you'd have all these different shapes. And they also have it for 8 as well. Okay, an octahedral, where you have 6 bonded pairs, 5 and 1, 4 and 2, and they have all different shapes. But again, we're just going to deal with the first part. When I put your chart in there that actually has 2 pages, just worry about the first page. Because the second page is the 5 and the 6, and we're not going to deal with those, okay? And when you start dealing with double bonds and all that larger shapes, that's kind of a totally different thing. So VSEPR does not work for, like once you start doing organic and you have carbon chains of 3 and 4 and 10 and 12, nah, we're not, that doesn't work for it. That's just too much, okay? Here you've got, you know, you don't have a central atom anymore, and that's why VSEPR doesn't work for it, okay? Why does it work? Well, whenever you form a bond, remember you overlap orbitals. Orbitals are places where you find electrons. So if you overlap s orbitals, okay, they get a new shape and they look like these 2 guys combined. If you do p orbital, an s and a p, and then it's called an sp. Isn't that tricky? It just has a wider shape here. So when you see these different shape orbitals from what we did before, it's because now you're forming a bond. and you're going to get overlap, so you're going to get a little different shape. And again, not something we're going to spend a lot of time on. I don't expect you to understand or know all the shapes. Just know that if you form a bond, you have an overlap of orbitals. Depending on which orbitals you overlap, you're going to have different shapes. In other words, you're going to have different areas where you can find your electrons. Because remember, that's what an orbital is, a place where you find electrons. So their shapes aren't going to be spherical and all that. Okay? All right. If VSEPR predicts the shape of the molecules, it does a really good job. Okay? Does it fit the orbitals? Not so much. But again, that's not important. I'm not going to worry about that. So all we're going to worry about is the shape. Yeah, we're not going to worry about this stuff. Okay. I'm trying to think. Again, remember, hybrid orbitals is a mixing of the atomic orbitals, and then you end up creating new orbitals. They're a little different shape. But again, an orbital is still a place where you find two electrons. You know what? I think that's all we need for this chapter. Well, hybridization is the mixing of the orbitals. So we're going to quit right there and be done. Chapter 9, only one part. Cool beans, right? All right.